السلام عليكم ورحمة الله وبركاته. النهاردة إن شاء الله هنشرح Chapter 1 لمنهج ال IGCSE Chemistry Cambridge OL. الchapter ده أو الشرح ده هيكون مناسب ل Grade 9 and Grade 10. بالنسبة للجزء ال Extended الخاص ب Grade 10 فده I'll point it out when we reach it. So if you are watching us at Grade 9 you can follow along. Chapter 1 talks about the particulate nature of matter. So we start with a question. What is matter? Matter is anything that has a mass and occupies space. And in our universe, all of our universe is made of matter in different states and in different sizes and shapes. Matter is made of particles that are too small to be seen by naked eye. We'll call these atoms. Particles have energy that makes them vibrate continuously, so all particles are in a continuous state of motion. Regardless to the state of matter, whether it's solid, liquid, or gas, the particles are always moving, even if you can't see them move. Particles move and collide in all directions, and this movement is called the random motion or the Brownian motion or the Brownian movement. We'll talk about that in a little while. So, we have three states of matter. Any matter can exist in one of these three states, either a solid or a liquid or a gas. If we look at these three pictures, we can see a diagram representing how the particles are arranged in each of these states. So if these circles represent the particles of a solid, as you can see, they are firmly attached to each other. There are very, very small intermolecular spaces that are actually negligible. We can say that they don't even exist. These particles are so firmly attached because the intermolecular forces between these particles are so strong. These particles are closely packed and arranged in a crystalline lattice. This shape or this diagram representing how these particles are arranged is called a lattice. So a lattice by definition is a regular three-dimensional arrangement of atoms or ions in a crystalline solid. We'll talk about atoms and ions later on in chapter 3. So, because these particles have very small or negligible intermolecular spaces, they have a fixed shape and a fixed volume. Also, the intermolecular forces between them prevent these particles from moving freely. So again, they have a fixed shape and a fixed volume. We talked about the intermolecular forces. They are very strong. Even though these particles are firmly attached, they still move, but their motion is very limited. These particles vibrate in position. Because of all these characteristics of particles in solids are very, very hard to compress. Now, we sometimes say that they can't be compressed. Moving on to liquid, as you can see, the particles are kinda randomly arranged. They are still close together, but not as close as they are in a solid. And there are quite larger intermolecular spaces. The intermolecular forces as well are weaker than those in solid. Therefore, a liquid has a fixed volume, but as for its shape, it takes the shape of the container because the particles are allowed to move and take the shape of the container. As I said, the intermolecular forces between the particles are weaker than in solids, which allows the particles to move and slide past each other. As there's a small chance, or it's not that small actually, but as the particles are allowed to move, even if it's a limited motion, we can say that liquids can be compressed, even though it's quite hard. But it's possible, unlike solids where it's impossible to compress them. Now moving on to gases, as you can see, the particles are so far apart and they are very randomly distributed. So a gas doesn't have a fixed shape or a fixed volume. The intermolecular spaces are very large and hence the intermolecular forces are very weak, if not negligible. The particles move and collide in all directions, and that makes the gas easily compressed. So, now we are going to talk about the changes of state based on the kinetic theory model. This part is a part of the extended curriculum for grade 10. So, we have a solid and we want to change it into a liquid, or we have a liquid and we want to change it into a gas, or we have a gas that we want to change into a liquid, and a liquid we want to change into a solid. So this is basically the change of state, but we're going to explain that using the term particles. If we have a solid and we heat that solid, the particles gain more energy and vibrate more. This makes the solid expand. Why? Because the particles are moving further apart from each other. At the melting point, the particles vibrate so much that they overcome the intermolecular forces between them and break away from their position. And then the solid turns into liquid. So as we can see here, we have a solid with its particles arranged in a lattice, small intermolecular spaces, strong intermolecular forces, and we heat that solid. So the particles start to vibrate and the size gets larger. When we heat more until we reach the melting point, a liquid is formed. As you can see, there is still small intermolecular spaces and there are weak intermolecular forces, but the particles are allowed to slide past each other. And that's why this is a liquid and not a gas. The temperature of a pure melting solid will not rise until it has all melted. We'll explain that when we reach the heating and cooling curves in a few minutes. When the substance has become a liquid, there are still very significant forces of attraction between the particles, which is why it's a liquid and not a gas. Now, to defining the melting point. The melting point is the temperature at which a solid begins to liquefy. As we mentioned, pure metals have sharp boiling points, meaning that it happens at a particular temperature. And again, we'll explain that in a minute. If the liquid is heated, the particles will move around even faster as their average energy increases. Now, to heating that liquid. So we heated the solid until we reached the melting point and it turned into a liquid. Now we're gonna heat that liquid, okay? So if this liquid is heated, the particles will move around even faster as their average energy increases. Some particles at the surface of the liquid have enough energy to overcome the forces of attraction between themselves and the other particles in the liquid, and they escape to form a gas. So the energy of the particles of a liquid aren't actually evenly distributed. The energy of the liquid particles at the surface can be higher than those in the down part or the inside of the liquid. So the particles on the surface have more energy, so they can break away from the other particles of the liquid. And when that happens, the liquid begins to evaporate as a gas is formed. We have another definition, which is the boiling point. The boiling point is the temperature at which a liquid starts turning into a gas. We can define it in another way, saying that it's the temperature at which bubbles of gas actually start to form inside the bulk of a liquid. You know, when you're making a cup of tea and you heat the water, it starts, after some time, starts making bubbles in the liquid. At that temperature, this is the boiling point for water, when these bubbles start forming in water. Or you can just define it at a temperature at which a liquid starts turning into a gas. Now, the evaporation. Evaporation is the process in which a liquid changes into a vapor or a steam. Of course, steam is for water. Water turning into water vapor or steam. At a temperature below the boiling point. Below the boiling point because, as we mentioned, at the surface of the liquid, the particles have more energy, so with a small bit of heating they can break away from the other liquid particles near them, starting to form a gas. Okay, so now we have a solid turned into a liquid and a liquid turned into a gas. Now we want to reverse this process. So we start with a gas. Now we want to turn that gas into a liquid. When a gas is cooled, the average energy of the particles decreases and the particles move closer together. That's the opposite of what we did when we tried to transform a liquid into a gas. When we try to transform a liquid into a gas, we heat it. But here we are cooling. So we are decreasing the energy of the particles and making these particles move closer together. When these particles move closer together, the intermolecular spaces get smaller and the intermolecular forces get stronger. So the gas turns into a liquid. The forces of attraction between the particles now become significant and cause the gas to condense into a liquid. Condensation is the change of a vapor or a gas into a liquid, which is accompanied by the evolution of heat. So turning a gas into a liquid is followed by heat evolution. Now we have a gas turned into a liquid. Now we want to turn that liquid into a solid. So we do the same thing. We cool that liquid, or in other words, we freeze it. When a liquid is cooled, it freezes to form a solid. And again, the particles of the liquid move closer, even closer to each other. The intermolecular forces increase, the intermolecular spaces decrease, and the liquid is turned into a solid. We'll see an example right now. Let's take water. So we start with solid water, ice, and we melt it at 0 degrees Celsius because ice in nature has a temperature below 0. So we have ice and we put it at 0 degrees Celsius. It starts melting and starts turning into water, which is a liquid. If we warm that water up, some of it evaporates and the rest boils at 100 degrees Celsius, and then it turns into a steam, which is a gas. Okay, so we have a melting point for water, which is 0 degrees Celsius, and a boiling point for liquid water, which is 100 degrees Celsius. Now to reversing the process, we have a steam which has a temperature over 100 degrees Celsius. If we cool it below 100 degrees Celsius, the water vapor begins to condense or liquefy, turning into water. If we cool that water, it freezes or solidifies. At 0 degrees Celsius, it turns into ice. What do we notice? That both the melting and freezing points of water are 0 degrees Celsius, and both the boiling and condensing points for steam or for water are 100 degrees Celsius. It just depends on the direction of the energy. Are we heating or are we cooling? Now to some notes. The melting point and the freezing point are equal for any substance. As I mentioned, it's just depends on the direction. Are you heating or cooling? Solids, which have stronger forces of attraction between their particles, have higher melting points as they require more energy to break these intermolecular forces and turn into a liquid. So of course, not all the intermolecular forces of solids are the same. Some solids have stronger intermolecular forces than others. So the stronger these intermolecular forces are, the more energy we need to break these forces. Liquids with high boiling points have stronger forces between their particles than liquids with low boiling points. Just the same idea as the solids before them. So we talked about melting, evaporation, condensation, and freezing. Right? There is another phase change called sublimation. Sublimation is when a solid turns directly into a gas without forming a liquid. And it's the vice versa process as well, when a gas turns directly into a solid without passing by that liquid state. So sublimation is the direct change of state from solid to gas, and the reverse process, meaning from gas to solid. We have some examples for solids that sublime. We have iodine, which is a dark gray solid that sublimes to purple vapor, the iodine gas, and if we cool that iodine gas, it turns into that dark gray solid directly without forming a liquid. We have dry ice, which is carbon dioxide in a solid state, and it's a white solid, by the way. It sublimes to carbon dioxide gas directly, and if we cool the carbon dioxide gas, it turns into dry ice directly without forming a liquid. We have also naphthalene, which is mothballs, and ammonium chloride, the sublime as well. The evaporation rate depends on a few variables. The surface area. If we have a larger surface area, the evaporation will occur faster. Why? Because the number of particles exposed to the higher temperature is more, meaning that these particles will gain more energy faster, and hence they will break the intermolecular forces attaching them to the other particles next to them, and they will turn into a gas faster. Having a lower surface area means that a larger number of particles aren't exposed enough to that high temperature, so they don't get the energy required for them to break out and form a gas. So larger surface area means faster evaporation. The temperature, of course, increasing the temperature means faster evaporation. Volatility. A volatile liquid is a liquid that has a relatively low boiling point and a high evaporation rate. So the more volatile the substance is, the faster it evaporates, because its boiling point is already low. So it doesn't require that much energy and heat to turn into a gas. The boiling point. A low boiling point means faster evaporation, which explains the volatility. The pressure. Decreasing the pressure means that we allow the gas to expand and have more space for it to move around. So these particles are allowed to get away from each other. So that increases the evaporation rate. Now back to the heating and cooling curves. So a heating curve represents the phase change when we apply heat to a substance. Okay? Here we have a pure substance. How did we know? We have sharp boiling points, we have sharp melting points, and boiling points. What do I mean by sharp? At 100 degrees Celsius, water boils, and it just stays at 100 degrees Celsius until all water particles have boiled. So this doesn't happen over a range of temperature. Same here in the melting. So once melting starts, as in here, the temperature stays at 0 for a while, a few minutes in here, as you can see, like a minute and a half or something, until all the ice has melted. When the water starts to boil over here, the temperature stays at 100 degrees Celsius until all the water has turned into steam. So the melting and boiling points are clear and sharp, as they are not happening over a range of temperature. They happen at a certain temperature. Now let's look at an impure substance. As we can see, the boiling and melting just happen over a range of temperature. So the change of state for an impure substance occurs at a range of temperature for each stage. That's due to the presence of impurities, which require different temperatures for them to melt or boil. So the melting and boiling and the entire change of state, either from solid to liquid or from liquid to gas, happens at a range of temperatures. So it doesn't boil or melt exactly at 100 or 0. No, it can boil over a range of temperature from, let's say, 100 to 150, or melt from 0 to 90, for example, or 0 to 50, something like that. That's just an example. Okay. Now to a cooling curve. A cooling curve is the opposite of a heating curve. It just shows how the temperature of a substance changes with time as we cool it from a gas to a solid. So now we have a cooling curve for a substance. We'll start with a gas at a very high temperature, like 78 degrees Celsius. We cool it, and it's a gas, and at 79 it remains as a liquid right here. Sorry, it's a gas, and at 78 it remains as a steam until all the particles have turned into a liquid. And then when we cool it even more at -15, it stays at -15 until all the particles have turned into a solid. So this doesn't happen over a range of temperature. The condensation point is 78 and the freezing point is 15. I think this video is already running quite long, and so I'll split this chapter on 2 videos. If you like this video, please don't forget to like and subscribe to the channel. It means a lot to me. And if you have any questions, just drop them in the comment section below, and I'll see you in the next video. Take care.